Hi everyone, here's a question about a bungee jumper, which is shown, the motion is shown in the graph on the left. The first question asks us to calculate the displacement and distance travelled after 50 seconds. So to do this, we need to work out the area under the graph. Now for displacement, that's a vector and it describes the position in relation to the origin rather than the total length travelled. So we have two triangles. One of them is positive because the velocity is positive. One is negative because the velocity is negative. So the first one is this one here. There. That's going to be a half times the base, which is 30, times the height, which is 10. Then the other one, which is this one here, the negative one, is a half times 20, which is the base, times negative 10, which is the height. So that negative is really important. And when you put this into your calculator, you should get 50 metres. Now the distance, you just ignore the negative sign for the velocity. So you just treat it like speed and time. So it's the same thing, so I've got a half times 30 times 10 for the first one, plus a half times 20 times 10 for the second one. And popping that into your calculator, you should get 250 metres. So this means that the total distance travelled by the bungee jumper is 250 metres. So that would correspond to the distance of going down and then the distance coming back up again. Whereas with the displacement, the bungee jumper finishes 50 metres away from their original location, from where they started from. Now, part B, calculate the acceleration at 10 seconds, 30 seconds and 45 seconds. So at 10 seconds, change colours, 10 seconds that corresponds to here. We just want to find the gradient of that part of the curve. So the gradient between 0 and 20 is all the same. So we can just do rise over run. So 10 seconds is going to be, the rise is 10 and the run is 20, which gives us a gradient of 0.5 meters per second because it's the acceleration. For 30 seconds, we have a negative gradient, so decelerating, and the gradient is the same between 20 seconds and 40 seconds. So we can use rise over run for that whole segment, or we could just choose a segment. So how about we just choose between 20 and 30. So here the rise is, it's going down, so the rise is 10, and the run is also 10, so that's minus 1 meters per second, and that minus is very important because that tells us that they're decelerating. And for 45 seconds, that's around here, so we can just use that segment of the graph. So the rise is 10 and the run is 10, so we just get 1 meters per second squared. And that's part B. Part C, sketch an acceleration time graph. So now we know the acceleration of each segment, each of the 3 segments of the graph. So we can just plot that. So we need to put some numbers on our graph. So we'll go 10, 20, 30, 40, 50. Between 0 and 20, our acceleration is positive 0.5. Between 20 and 40, so here's 40, our acceleration is negative at at negative 1. And sorry, my scale, it's not to scale. It's because I run out of room on my screen. And then from 40 to 50, the acceleration is again constant at 1. I'm going to stick that up there. And now we can join each segment of the graph together. Just remember that acceleration can instantaneously change, unlike velocity. And that can occur when we're speeding up and then we put the foot on the brake and we decelerate. So this graph is quite realistic. So, oh, that was meant to be part C there. Part D, when was he stationary? Well, he's stationary whenever the velocity is 0. So, when velocity is 0, so that will be, change colours here. So at 0 seconds, and that would be before he jumps. Again at 30 seconds, and again at 50 seconds. So you'd need to list them. So it's 0, 30, 50 seconds. And then when was his acceleration constant, but not 0? So that'll be in each of those sections. So it's wherever the velocity time graph is linear, we'll actually give an acceleration that's constant. So we can actually just say all times there. But it's important to note that if you've got a linear velocity graph, then your acceleration is constant. When was his velocity constant but not 0? Well, velocity was not constant at any point. When they ask for constant, we're looking for part of the graph which has a 0 gradient. So that's never. And that's how you do one of these questions.